Yeah, thank you very much, Leon, and also yeah, for the invitation and yeah, for hosting this and organizing this everything, right? Yeah, throughout the talk, please, if there are any questions, don't hesitate in asking them, right? Because I'm not really sure what the background of everybody is and how much everybody already knows about Stein variation and gradient descent. Oops, what's happening now? Okay. Yeah, so let me start by saying that this is joint work with Andrew Duncan from Imperial College, with Lucas Szpruch from the University of Edinburgh, and then also with Mikhail Renger more recently from the Weierstrass Institute in Berlin. And this was funded by the University of Potsdam and by two collaborative research centers, CSC 1114 and SFB 1294, and also the Alan Turing Institute in London. So let us start by looking at the motivation. What is the goal? So the goal is, generally speaking, to approximate probability distributions in high-dimensional spaces. And more specifically, the typical situation is that there is a potential function given from Rd to R, as written here. And then the goal is to approximate the probability measure pi that is associated to this potential function V as, let's say, the Gibbs measure like this. And okay, Z is the normalization constant that makes this a probability measure, and it's typically intractable. And what you should think about from an algorithmic perspective is that this function V can be evaluated pointwise, and also its gradient can often, or in the applications that we have in mind, be evaluated pointwise. And yeah, evaluating or approximating probability measures of this form has many applications, and most importantly in Bayesian inference and in molecular dynamics. There are different ways of going about approximating probability measures of this form, but in this talk I will concentrate on particle-based approaches in a broad sense, let's say. So pi can be approximated in this form as a sum of Dirac measures centered at the positions xi. And then, of course, the question is how to find appropriate positions xi in Rd. Yeah. So let us just start with two examples, right? This is maybe the overdamped Langevin dynamics. You can see the cursor, right? Yeah?
Yes, we can see the cursor.
Okay, thanks. So this is a typical example and it's often used. It's actually not a many particle system. You can think it's just one particle. It's a stochastic particle though. And yeah, and the probability measure pi will then be approximated in terms of, say, the law of this randomly evolving particle. I will discuss this below here. And yeah, I guess it's no surprise that the main topic of this talk is this Stein variational gradient descent algorithm, which can be written in terms of a coupled system of ODEs. So we have n particles, and every particle has the position xi, and I runs from 1 to n. And then it follows this dynamics, interacting with the other particles xj. And an important ingredient for this dynamics is the kernel function k. I'm going to say a few more things later on in the talk about precise mathematical assumptions on this. But until now, it is sufficient to think that this, in some sense, mediates the interaction between the particles xi and xj, for instance, here. Okay, there are certain similarities between these dynamics, right? Well, let me first say that if you define from these dynamics, both the stochastic dynamics and the deterministic dynamics, we can define associated probability measures. So for instance, in terms of the Langevin dynamics, we can look at the law of X, or we can look at some sort of ergodic average, which is, let's say, more relevant algorithmically, because when using this as an algorithm, you would discretize this dynamics and then evaluate, for instance, test functions that you want to, the integrals of which you want to compute against the measure of interest. You would do this by appealing to a long-term ergodic average of this form. So these would be the measures kind of coming out of this dynamics, the overdamped Langevin dynamics over here, and then the Stein variational gradient descent produces a measure that is just given by the empirical measure associated to the particle system like this. Okay, and then in an appropriate sense, we've got this convergence in long time for Langevin dynamics, or for long time and when the number of particles goes to infinity, to the measure pi of interest. And this, of course, then provides us with a computational recipe of actually approximating this measure pi, right? Because we can discretize these dynamics, we can use many particles and run these dynamics for a long time. And then, although these results are not stated here in extremely precise form, these results will then guarantee that pi is approximated in some sense. Okay, of course, these are quite different now from the outset. This is only one particle. This is n particles. There is only deterministic dynamics in the Stein variational gradient descent, and the Langevin dynamics is stochastic. But anyway, you can kind of see that the structure is similar. In both dynamics, we've got a term that is associated to the gradient of V. So that drives the corresponding probability measure towards, let's say, the minimum of V, and this translates into high probability regions of pi. And then there's also this repulsion term. It's maybe not completely obvious from this definition, but this will lead to a smearing out of the corresponding measure. And similarly, this added noise here will have a similar effect, because if you add noise to the dynamics, the corresponding probability measure will become wider, right? Now, one way of looking at these algorithms is through the lens of PDEs, let's say. I mean, there are various other ways, of course. But let us start here with the viewpoint of PDEs, and in particular, maybe transport PDEs. So the law associated to the overdamped Langevin dynamics here satisfies classically the Fokker-Planck equation, and the two terms that I just talked about are represented in this drift and diffusion contribution in the parabolic PDE. And similarly, the empirical measure corresponding to the SVGD deterministic interacting ODE system satisfies weakly the so-called Stein PDE, which importantly includes this convolution operator. So this is an important notation for the talk. This convolution operator depends both on the kernel K and the measure rho. And the corresponding equation will then be sort of a mixed equation, integral differential non-local equation, right? Involving both derivatives and an integral. Okay, and then the similarity between these dynamics is expressed through this reformulation here from the maybe more usual way of writing the Fokker-Planck equation. And then this is just sort of a reformulation of this, but this gives a different interpretation of the dynamics. So in particular, both of these equations, when written in this form, can be thought of as transport equations, right? Because they have this form dt rho plus the divergence of rho times the vector field that depends actually on the measure is equal to 0. And equations of this form have a very clear and direct physical interpretation, namely that they describe the transport of probability mass. Let's say at time 0, the probability mass is distributed according to rho 0. And then it is moved around by the vector field V. And every particle sort of this probability distribution follows the vector field V. And then the corresponding evolution of the densities of probability measures is described by this continuity equation or transport equation. So you can think of, and then of course these red terms here represent exactly these vector fields V. Yeah, again, although this is equivalent mathematically, this is of course the same PDE. Here, the interpretation is there's some stochastic system behind, and here the interpretation is that the probability mass is moved around by a vector field. And actually, yeah, Simon has some very nice work on this, developing algorithms based on this reformulation. Okay, so and just in general, there has been in Bayesian inference this interpretation of using vector fields to transform probability measures is known, let's say, as the transport approach to Bayesian inference, where you can, for instance, transport the prior to the posterior through applying an appropriate vector field V. Okay, now.
Sorry, Nikolas. So why do you write V of rho if there is also the derivative of rho? Maybe I just got late. Maybe I'm missing something. I see in these equations there is a gradient log d rho dp.
Yeah.
So we write V of rho. It should be V of rho and the gradient of rho.
Yeah.
Okay, I understand. So you mean that V depends on rho through this kind of gradient dependent?
Yes.
Okay.
Yes, exactly. Thank you very much. Yeah. I mean, actually, sort of one of the tricks in this SVGD PDE is that you can, using integration by parts, actually avoid the dependence on the gradient of rho. And this is sort of a computational trick why this can work nicely in practice. But you're completely right. So yeah, thanks. Okay, other questions? Okay, then, okay, so these PDEs have nice interpretations in terms of gradient flow. So what's a gradient flow? At least intuitively. Okay, so a gradient flow, let's say for this talk, we think of it as being determined by two ingredients. That is, there is an energy functional, let's say, that describes this valley. So this parabolic function here, this is a sketch, right? This would be a functional that depends on the measure rho, right? And in this talk, this will always be the KL divergence or relative entropy between the target pi and the measure rho, which we currently look at. Okay, given here. And then, second of all, to define the gradient flow, there needs to be some notion of taking the gradient. And you can think of this notion being determined by a certain geometry of the underlying space. So in particular, this is at least heuristically, or was heuristically introduced by Otto in the 90s. By the idea that, at least heuristically, the set of probability distributions on RD can be thought of as a Riemannian manifold. And then when he especially considered this, this set of probability distributions to be equipped with the Wasserstein metric and the corresponding Wasserstein metric tensor heuristically. And in this Riemannian geometry, you can compute or you can, this naturally induces a gradient operation. And yeah, for instance, one way of seeing that really the gradient flow is determined by these two ingredients can be seen. This was also done by Otto. That you can sort of formally this equation can be discretized as an implicit Euler scheme, and this would lead to a way of computing iterates of the solution rho I iteratively. And this involves two terms, namely the KL divergence and then the metric that we need to consider. Okay, so this statement here below makes it a bit clearer what's really the relation between the overdamped Langevin dynamics and the Stein. Namely, both are gradient flows and they share the same driving energy function. So they both can be expressed in terms of the KL divergence or the relative entropy. And of course, there has to be a difference, and the difference is exactly due to the underlying metric structure on the set of probability distributions. Okay. So both Langevin and Stein can be expressed as gradient flows of the KL divergence, but with respect to different distances on the underlying space. In the Langevin case, this is, as Otto famously found, given by the quadratic Wasserstein distance. And here you see the reformulation of the quadratic Wasserstein distance in terms of the well-known Benamou-Brenier formula. And this means intuitively that the distance between mu0 and mu1 is given by the least amount of work or kinetic energy, if you think of this v squared as measuring the kinetic energy, transporting one of the measures to the other one, right? And this is measured in the L2 sense. In the Stein sense, in the Stein, for constructing the Stein dynamics, actually the only thing that we have to do is to consider a similar transport-based distance. So transport-based distances are basically defined in this way, where the distance between two probability distributions is given in terms of a vector field that transports one of the densities into the others, according to this transport equation here. And then the cost of this transport is measured in some way. And traditionally, okay, this is done by the L2 way, in the L2 sense, giving rise to the Wasserstein distance. And if we replace this L2 by this reproducing kernel Hilbert space norm, which I will discuss on the next slide, we get this new distance. And yeah, and then basically how this works is that these transport distances, this is also Otto's interpretation, because you minimize over connecting paths between mu0 and mu1. If you adopt this idea that the underlying space of probability distributions can be thought of as a Riemannian manifold, then this would be the length of curves connecting points in the Riemannian manifold, and the shortest path connecting these points would be the geodesic. So this would be the geodesic distance associated to a Riemannian manifold. In general, and maybe this is more of a sort of a vague thing to say, but it's maybe an outline for a research program or so. If you want to construct algorithms that can approximate high-dimensional probability distributions, then you can start by choosing a cost functional and a distance on the set of probability distributions on this P. And these two ingredients, 1 and 2 together, will determine the gradient flow, and therefore corresponding PDE. And then if you can come up with a suitable simulation scheme, so recall the SDE for Langevin dynamics or the interacting particle system for SVGD, then this is likely to result in a nice algorithm that can be used in these cases. Okay. Yeah, so this picture, I just made it to indicate the fact that somehow the geometry on this underlying space is altered by introducing this new distance, and you can see that somehow maybe some curvature properties will change and so on. Okay, and with it also the corresponding path that the PDE takes. All right, so this slide is just a crash course on reproducing kernel Hilbert spaces, which contains everything that you need to know for this talk. So we're talking, of course, about these interaction functions K that mediate the interaction between two particles. And they can be thought of as some sort of, yeah, let's say infinite dimensional positive. Actually, I should have written semi-definite here, semi-definite matrices. So whenever you plug in points like this and build matrices like this, then the main assumption is that this will lead to a semi-positive definite matrix. The main example being a Gaussian kernel of this form with a certain width parameter sigma. And then what is of course most important now is that to such a function K, there exists in a natural way a corresponding so-called reproducing kernel Hilbert space HK. And it, roughly speaking, consists of limits of functions of this form. So you fix one of the arguments of the kernel and let the other one free, or this is the argument of the function x. And then you consider linear combinations and limits of this. And what you can see immediately from this way of thinking about RKHS is that functions in this reproducing kernel Hilbert space are expected to inherit properties of the generating kernel K. So for instance, if the kernel is smooth, then also all the functions in the RKHS will be smooth. If all of them are bounded, then all of these functions will be bounded. And so I think this is a good way of thinking about the space. Then we need to construct this norm, and it is constructed from these coefficients. And this is not of course obvious, but usually we have that this space is embedded in the L2 space with a stronger norm. So typically also much stronger. So this could be, for instance, a Sobolev space. And there are also results showing that in general, these spaces or these norms on these spaces can be thought of as including higher order derivatives in the norms. Okay, so this was the slide basically explaining this. Yeah. Let's see what the next slide says. Now, one of the points of this work was to analyze the Stein PDE. So the PDE that describes the movement of the particles or the empirical measure. In particular in the limit as n goes to infinity. And using this idea that one can use this gradient flow geometric ideas, okay? And this slide, I'm not going to go through all the constructions, but this is to give some flavor of how some of the constructions arise, right? So we are meant to think of these probability distributions rho as points in our Riemannian manifold. And then we think in terms of these transport equations, right? So these measures are moved around by a vector field V. And now you can see that if there is a curve rho t fixed, then the driving vector field will not be unique. So given a curve rho, V is not unique, precisely because this operator here has a kernel, right? You can, to any V that satisfies this equation, add another vector field, which is weighted divergence free. And so uniqueness holds only up to addition of weighted divergence free vector fields. And what is typically done is that you can then demand that some norm of this V is minimal. This, of course, is directly related to these formulations over here, where these, when you look at these geodesics and connecting paths, then these ideas of considering minimizers actually appear naturally. And then the question is, what can one say about driving vector fields V that are minimal in either the L2 sense or the RKHS sense? And in the L2 sense, it is well known that vector fields that are in fact gradients of scalar functions are minimal. So in other words, even if I don't give you the curve rho t, I can already tell you that any vector field that is minimal in the L2 sense will necessarily be a gradient. And this is exactly where the Stein geometry and the SVGD dynamics really differs from the L2 picture and the Langevin and the Fokker-Planck picture. Because if we consider instead of the L2 norm, the RKHS norm introduced on the previous slide, then actually these optimal vector fields will not be gradients anymore, but they will have this kind of structure. So this is also, of course, a much smaller space than sort of the space of, let's say, all smooth vector fields. But they are not gradients. They are gradients passed through this integration operator, which I recall is a convolution operator against the kernel K and the measure rho. And yeah, one particularly nice way of thinking about it is in terms of Helmholtz decompositions. So the Helmholtz decompositions in the L2 sense says that any vector field can be decomposed in a divergence-free vector field and then a gradient. And a similar Helmholtz decomposition can be written down in the space HKD. Well, I didn't explain this too much, right? I mean, on this slide, I introduced reproducing kernel Hilbert spaces, which were composed as scalar valued functions, but now we are interested in driving vector fields. And so we are taking, say, the D-tensor product of these functions to get spaces of vector fields. Okay, so in this space of vector fields HKD, we can perform Helmholtz decompositions, so orthogonal decompositions in weighted divergence-free vector fields, and then the equivalent of gradients as in the L2 sense. And this, yeah, intuitively maybe explains why this operator TK rho all the time shows up in the constructions. So for instance, we can define the tangent space. So the tangent space should be, should contain elements which can modify in these transport equations additively the measure rho. And these elements are precisely given by those elements that actually have this form TK rho and then a gradient, as suggested by this minimization argument, right? So for any probability measure rho, we can define a tangent space like this. And importantly, also equip it with the corresponding inner product, so that formally we obtain a Riemannian manifold like this. Yeah, so this construction fits nicely with the Stein PDE because, as you can see, these vector fields that drive the Stein PDE are always in this space, at least formally, and then the quantities that are obtained in this way are actually appear here as derivatives of the rho. So this is how this construction goes about. And then, having set up this tangent space structure equipped with the Riemannian inner product, we can then go on and use Otto's machinery. So the idea is, once there is this formal Riemannian structure on the space of probability distributions, we can use ideas from Riemannian geometry and at least formally compute gradients and geodesics and so on. And yeah, so the main idea of this work was then to use this so-called autocalculus to actually say something about the rate of convergence for the Stein PDE. So I will now come to how this works, right? First of all,
can I ask a quick question?
Yes, sure.
So if you look at a textbook from differential geometry, then the tangent space is defined in a very basic way as being, this velocity of curves on the manifold. But you, am I correct that you are not constructing the, let's say, real tangent space, but you single out at each point the tangent space with minimal norm? Is that correct?
No, that's so okay. That's thanks for the question. So what I'm kind of doing by this singling out these vector fields with minimal norm is to basically give a one-to-one correspondence between vector fields here and changes in the row here, which is kind of necessary if you want to do the calculations that appear later on, right? So you can think of it like if you want to think in terms of basic Riemannian geometry, then fixing elements of minimal norm, this will give a parameterization of the tangent space, right? If you don't constrain yourself to elements of minimal norm, then this map from V to dt rho will not be unique. I mean, there will be different V's giving you the same dt rho. And so this doesn't parameterize the tangent space in the proper way. I don't know, did this answer the question somehow?
Yes, I think so. Thank you.
Yeah, thanks for the question again. Okay, and of course, kind of the point of this is sort of introducing this new parameterization of the tangent space is that the Riemannian product can be conveniently expressed in terms of the vector fields, right? So more conveniently, I mean, you can also somehow describe it. You could somehow describe it in terms of the changes in the row, but it's much more complicated. So, or let me say, like the Riemannian inner product is naturally given in terms of the vector fields. So in terms of this representation, in terms of the vector fields instead of the changes in the row, right? Okay. Now we're interested in geodesics. I will explain on the next slide why the geodesics are interesting, right? But these geodesics or unit speed geodesics, these are solutions to these, where am I now? A little bit too fast. Okay, so these are basically minimizers of these problems, right? So we're looking at curves that are minimal in the sense that they connect the measures mu0 and mu1 in the most efficient way. Okay, and then we can do this, so we can come up with the formal optimality conditions for these infirmizers. And in the Langevin case, this is classical. So these optimality conditions in the Langevin case consist of the continuity equation again, and of so this is an HEB equation from optimal control, which makes sense because if you have a geodesic, so you need to steer the geodesic in an optimal way to come to the correct final condition, right? And similarly, these are the optimality conditions for the Stein PDEs. So these equations, of course, kind of look similar and they have similar interpretations. We have this continuity equation, but including the driving vector field of this form, which again, the fact that we have this TK gradient is due to the fact that exactly these kind of combinations are minimal in the reproducing kernel Hilbert space norm, and in the geometric sense or give rise to elements in the tangent space. And then there is a control kind of equation, right, which is quadratic in the gradient of psi. So what's interesting about it is that here in this case, these geodesic equations are coupled. So here you can solve this equation by itself for psi because it doesn't depend on the measure on the curve mu, but this is not the case here. And this is in fact related to the fact that the Stein or SVGD system is an interacting particle system. Okay, so what can we do with these geodesic equations? One of the main ideas or motivations of this autocalculus was to describe the rate of convergence to equilibrium for PDEs that can be described in terms of gradient flows. And the intuitive description of this idea is here, right? So remember this picture, we've got the energy functional, the KL functional, and we've got the underlying space of probability measures. And then intuitively, I think it is clear that the convergence towards equilibrium will be faster if the space is somehow more curved, right? And it will slide down the valley faster. And so the way to measure this also depends on the underlying geometry here. And the way to measure this is actually to look at an appropriate notion of convexity, and the appropriate notion of convexity is this here, right? So you look at the second derivative, but along solutions to the geodesic equations. So we look at geodesics here in the underlying space, and then here we evaluate them on the energy functional, and if this is bounded below by lambda, so this is lambda convex, right? Then we expect a rate of decay with at least the constant lambda to the equilibrium. And this, I mean, maybe I haven't stressed this enough, but this is of course quite important for computational purposes, because we would like the algorithm to proceed as fast as possible. Yeah. Are there questions about this? Okay, so then, yeah, we can do these calculations using the geodesic equations obtained before. And yeah, maybe I shouldn't say so much about this. I think it suffices to say that the result is fairly complicated, and actually it's not easy to establish a bound like this. So what we did instead was, so the Hessian is here introduced because it is the natural analogon to the Hessian in the Riemannian case, right? Measuring the second order derivatives. And so it is maybe interesting. I mean, it would be very interesting to understand these expressions more deeply, but yeah, in order to simplify this a little bit, we looked at the curvature at equilibrium, so setting rho equals to pi. So this means basically linearizing the original PDE around the equilibrium pi. And this, maybe not surprisingly, leads to a certain functional inequality, which you would also obtain if you would first linearize the original PDE and then look at the spectral gap of the corresponding differential operator, right? So if the corresponding differential operator and the linearized PDE has a spectral gap, then you would expect exponential convergence to equilibrium close when the starting position is in fact already close. And okay, so this functional inequality looks a little bit like a Poincaré inequality in the, which is the equivalent or the analogous inequality for the Fokker-Planck-Langevin case. What is interesting though is that this quantity can be expressed in terms of the dual. I haven't really talked about this here in this talk, but next to the tangent spaces, we can also introduce cotangent spaces. And yeah, this has interesting geometrical implications. And here I also use it as a shortcut, right? So, okay, so what have we done now? We've simplified our investigation a little bit by looking close to equilibrium. And what happens is then we can study this functional inequality. And okay, I will come to this in the next slide. This functional inequality is actually not easy to satisfy with lambda bigger than 0. And this is because sort of here you can spot this k appearing and this integral operator appearing. And if k, for instance, is smooth, then this will be a compact operator. And the compact operator will push the spectrum to 0, preventing actually a functional inequality of this form. So that's an important property, or that's an important idea. Still, what might be interesting in practice would be to look at different kernels. So imagine you want to set up the algorithm and you want to decide, do you want to use kernel 1 or kernel 2, right? And at least close to equilibrium, it seems desirable to choose a kernel k such that this quantity here is as large as possible, right? Because then you can hope to find a bigger lambda here, promising a faster convergence to equilibrium. So in other words, we want to compare these expressions for different kernels. And there is a nice characterization, or at least there is a nice way of checking this. You can compare these quantities directly in terms of the corresponding functional analytic geometry, namely if the corresponding reproducing kernel Hilbert spaces are included in each other, and also the balls, the unit balls, are included in each other in this form. So if the K2 ball is included in the K1 ball, no, the other way around, right? If the K1 ball is included in the K2 ball, then this important expression is also bounded in this sense. So what you want to do is to make actually the choose a kernel that is as large as possible, right? Okay. And this basically means, intuitively speaking, that the kernel should be chosen as rough as possible. So you don't want to actually use smooth kernels, at least according to this theory, because as I said before, the functions in the space will inherit properties from the associated kernel. And therefore, if you use a very regular kernel, the corresponding space will be quite small. And so this quantity is also then expected to be quite small, and the corresponding lambdas are also expected to be quite small. Okay. Intuitively, maybe again, the idea could be to choose a kernel that has a sort of a kink at 0, driving the particles away from each other. So these are two results analyzing this functional inequality. One showing that actually, so the first lemma actually shows that it's not easy to satisfy this functional inequality, namely if the kernel is smooth, then actually this functional inequality forces lambda to be equal to 0, so there will be no spectral gap close to equilibrium. And this again, if you want to think in terms of proof, this is related to the fact that if the kernel is smooth, then there will be a compact operator here pushing the spectrum of this expression to 0. And similarly, you also might not want to use translation invariant kernels, because this will also, by an application of this functional inequality, lead to lambda equals 0. Okay. This is just an example, right? So if you're prepared to violate both conditions, so smoothness and translation invariance, then you can, in fact, construct a condition where this functional inequality will hold. Yeah, and you see that this kernel violates both conditions, so you should somehow adapt the tails of the kernel and also employ a kernel that I talked about before that is non-differentiable right here, and that has a little kink at the diagonal x equals y that will push the particles away from each other. And then choosing a kernel like this will actually result in a positive lambda in this functional inequality, so that we expect exponential convergence to equilibrium close to equilibrium. Okay, so I guess in the remaining 3 minutes, I will just make a little advertisement for some work with Michael Renger, which is not quite an archive yet, but hopefully this week or early next week, which is about finite size effects. So until now, we've mainly spoken about the Stein PDE, and this is mainly concerned with the case when the number of particles is already infinity. But of course, for algorithmic purposes, and so in this previous work, we've mainly studied the convergence properties when t goes to infinity. But of course, for the algorithm, it's also very important what happens for a finite number of particles. And so one interesting way of studying this is to actually add some extra noise to this SVGD dynamics. So this part here is the usual ODE that we had before. And then we can add some extra noise here, which is designed in a very special way, namely so as to make the product measure on the joint stochastic system. So this system will have the dimension d times n, right? Where d is the dimension of the state space and n is the number of particles. And yeah, the product measure will be invariant with respect to this noise enhanced SVGD dynamics. And it's interesting to study the connections between the SDE and the ODE. So here I put some comparisons between the deterministic and the stochastic SVGD dynamics. The stochastic SVGD is more in the spirit of MCMC, right? So MCMC in Bayesian inference is the idea of setting up an ergodic Markov chain that will then produce expectation values of interest by long-time ergodic averages, right? And whereas deterministic SVGD, this is more in the spirit of variational inference. In fact, in the paper where it was derived, maybe I should have also said this more clearly, the way I presented it here with gradient flows, this was not the original way of deriving it. But the idea of deriving it was in the sense similar that the authors considered minimizing movement schemes. So this is similar to the tangent space constructed before. And considering such motions that in some sense would reduce the KL divergence as fast as possible, which is actually very similar to doing variational inference, where a variational family is posited that is a distribution containing some parameters. So these parameters would be the positions of the particles, and they are then optimized such as to achieve a good fit of the variational family with respect to the target. Okay. Now, stochastic SVGD, so this SDE system is exact, right? In the sense that if you wait long enough, you get the correct invariant measure, in fact. Whereas the deterministic SVGD system it will produce a fixed point, right? So the particles will start at some point and then they will move until they stop. And this will be an approximation of the target, but it will not be exact, of course, unless you take very, very, very many particles. And yeah, the connection between these two things is that as n goes to infinity, the noise contribution actually here becomes negligible. And this can be shown by saying that the corresponding mean field limit for the empirical measure is in fact the same. So how is it possible then to study finite particle effects for the standard SVGD scheme? We can try to measure the distance between the, let's say, the empirical measure associated to the SDE and the mean field limit. And if we can quantify in some sense this discrepancy, then this might give an idea on, since the stochastic system does not suffer from finite particle effects, this might give an impression on how far away the deterministic system is actually from being exact for a finite number of particles. In other words, maybe if you want to think of it in this way, implementing the stochastic system maybe has some drawbacks. So for instance, you need to compute this square root here. And also, of course, the spirit of the dynamics is a little bit different. So the dynamics will not stop at some point, but it will continue jittering, and you might not want this, right? But you're aware of the fact that the stochastic dynamics is actually for a finite number of particles exact in the t goes to infinity limit. And then since it might be computationally more tractable to use a deterministic system, how far is the deterministic system from the stochastic system, right? And yeah, we did this in this work with Michael Renger using the theory of large deviations. So the random empirical measure that is associated to the SDE satisfies a large deviation principle, and this large deviation principle is in the number of particles. And it is, yeah, so it is given in terms of this rate functional I, which depends on the curves in the, so which depends on curves taking values in probability measures. And so what we would like to do is actually have a situation where this convergence, right, the probability that rho n is close to rho is actually fairly large, even for a finite number of particles. And so this means we would like to have this large deviation functional to be as large as possible. And this depends on the kernel, and we can analyze it in terms of the kernel. Yeah. And so there are basically two results of this. So one of the results is more philosophical, namely that the large deviation functional can in fact be expressed, or is most naturally expressed, in terms of the geometry constructed in the talk, right? In terms of the Stein geometry. And this means in some sense that the noise that is added here is natural for the geometry of the mean field limit. And this is maybe not that well known in the theory of gradient flows, but this is some known phenomenon in statistical physics where fluctuations and large deviations and gradient flows are connected through connections like this. And on a more practical level, we can see that this large deviation functional, which I said should be, we would like to have as large as possible, can again be expressed in the regime where n is large and t is large, in terms of this quantity that appeared in the functional inequality before. And so this shows that both the limit as t goes to infinity and n goes to infinity in the regime where both are already large are actually determined by the same quantity. And so, yeah, I really need to come to an end. This is an illustration of this. So these are ODE fixed points of the deterministic system, and with different kernels. And you can see that using this kernels, the particles are spread out more evenly. And here, somehow the final distribution, the ODE fixed point, is not as regular. And this is exactly corresponding to this result, namely the reproducing kernel Hilbert space associated to this situation is quite large, and the reproducing kernel Hilbert space associated to this situation is quite small. And this can be directly traced back to this quantity here, which I showed. Maybe this was, of course, this was, I guess, quite fast, but this can be connected to this result, connecting these quantities and the RKHS balls. Okay. Yeah, this is sort of my last slide. I'm going to take 1 minute to say something about it. So this was more like philosophical work, let's say, because it connects the idea of large deviations and gradient flows. And this other work, which is hopefully going to appear soon, is taking a more practical approach, really developing an algorithm based on the interpolations provided by the Stein geometry in terms of Stein geodesics. For instance, when you want to interpolate from the prior to the posterior using the likelihood AT. And one reason why I wanted to at least briefly say something about this is that this is quite related to inverse problems, which I believe you guys are quite interested in, because you can think of this equation as an equation for the driving vector field tk rho grad psi. And it's an inverse problem knowing dt rho. So the algorithm can be developed using ideas from the theory of inverse problems. Okay. So I hope I haven't gone too much over time. That was it until here. Thank you very much for the attention.